trying to develop to optimize cable-stay bridges. So I will first give you an introduction about these structures, and then we will move to describing the methodology, which is based on the concept of parameterized fragility functions. And then I will show you how we can apply this procedure to a case study bridge. So let's start with an introduction on cable-stay bridges and on their seismic behavior. In the field of bridge engineering, the span is a key parameter in the choice of the bridge type. And here you can see a comparison between the possible spans for different bridge typologies and the optimal spans. We can also see that cable-supported bridges, which are suspension bridges, and cable-stay bridges, are usually implemented to overcome large spans. And my research is about cable-stay bridges, which gain increasing popularity in the last few decades because of their highly efficient structural performance, and because of their appealing aesthetics. So this graph shows the bridges which held the record for the maximum span. As you can see, the first modern cable-stay bridge is considered to be Strömsund Bridge, which was completed in 1955 and had a main span of 183 meters. And since then, the maximum span grew until now, when the longest bridge is Russky Bridge in Russia, with a main span of 1,104 meters. Cable-stay bridges consist of three main components. First, we have the deck, which might be built in concrete, steel, or it might be a steel concrete composite structure. Then we have the pylons, which can have these different shapes. As you can see here, for example, a H-shape, diamond shape, or A-shape. And then we have the cable system. So these different arrangements are distinguished by where the cables connect to the pylon. As you can see in the fan type, the cables connect to the tip of the tower. In the harp type, the cables are equally spaced along the pylon. And then we can have a semi-fan arrangement, which is an intermediate solution between them. In terms of load transfer mechanism, we can imagine that to happen as follows. So when a load arrives, the deck will bring the load to the cables, which will then transfer that to the pylon to eventually move it to the ground, to the foundation, and then to the ground. Here I listed the key features of the dynamic behavior of cable-stay bridges. They have high flexibility, lightweight, thanks to the efficient use of material, low inherent damping, and strong nonlinear behavior, even under service loads. This nonlinear behavior is due to cable sagging, to materials nonlinearities, and also to second-order effects that should be considered both for the analysis of towers and for the deck. And because of the high flexibility, these cable-stay bridges have a long period, which means that they are subject to a reduced peak response, a reduced peak acceleration in the response spectrum, which in principle make them good candidates to withstand earthquake. Nevertheless, the response of cable-stay bridges to dynamic loads result in large amplitude vibration of its components, which show to be quite sensitive to earthquake in several events during the 90s. For example, here you can see damages which developed at the connection between the deck and the tower, at the connection between the cables and the tower, or for example, at the base, which means that cable-stay bridges are vulnerable to earthquakes. And since they usually represent key links in the infrastructure networks, also requiring a really high investment of money to be built, we understand why and how we need to perform the best approach we have to design them, which for seismic design can be considered to be performance-based design. So performance-based design is a procedure that results in a structure which maintains a desired level of performance under different levels of earthquakes. Here you can see the procedure that was suggested by the Pacific Earthquake Engineering Research Center, which starts from the definition of a probabilistic distribution of the intensity measure, and then moves to performing detailed structural analysis to characterize the distribution of the engineering demand parameters. This probabilistic distribution is then implemented to calculate the damages, the probability of damage in the structure, and eventually, based on this, we can obtain some measure of loss that can be used for a risk-informed decision making. So this procedure is well established in terms of assessment. But if we want to use that for the design of new structures, we somehow need to invert this procedure to update the design and to perform it again until we achieve a satisfactory solution. The point is, how can we perform this updating? Usually in design, we have two approaches. The first one is a trial and error approach, which can be based, for example, on the experience of the analyst. Or we can implement a numerical optimization approach. Whichever of this way we choose is going to be really computationally expensive. And this is mainly due to the requirement to perform nonlinear time history analysis, which are really expensive for cable-stay bridges because they require the consideration of all the sources of nonlinearity that they have. Also, a significant part of the computation is required by damage analysis, for example, if we need to perform a Monte Carlo simulation. And then if we choose to perform optimization, we also need to take into account the cost of function evaluation, which is required to estimate the gradient of the function and to find the best solution. So in the next part of the presentation, I'm going to discuss with you how parameterized fragility function can be implemented to tackle these issues and to support the performance-based design of cable-stay bridges. Here I will first define you what parameterized fragility function are, and then I will discuss how we can practically implement them. These two steps in the performance-based design usually result in fragility functions. Fragility functions are these curves that give us the probability of demand being higher than capacity conditioned on the intensity measure of earthquake. And this is the traditional concept of fragility. Differently, the idea of parameterized fragility functions consists in conditioning the probability of damage not only on the intensity measure of earthquake, but also on the design parameters of the bridge, which are the ones we want to obtain to optimize the structure. So how can we obtain these parameterized fragility functions? We can follow a four-step procedure, which starts from an experimental design, implements the concept of metamodels, and ends up with the logistic regression. So now we'll go briefly through these steps before moving to the application. The first step consists in experimental design, and it aims at building a design matrix on which later on we will be able to conduct some form of regression. We first start with the selection of a suite of ground motions, which will be characterized by an intensity measure. And then we select design parameters for the bridge. For example, in this case, we might select to optimize the dimension of the cross-section of a tower. And then we assign to each one of these parameters a uniform distribution that spans between the parameters that we won't allow the change to happen. Based on this, we implement a Latinate per cube sampling to generate a large number of combination of parameters, which means a large number of different design combinations. And eventually, we join the matrix of the ground motions, of the intensity measure, and the matrix of design parameters to build the design matrix. The second step consists in performing structural analysis for each line of the design matrix. And in each time history analysis, we are interested in recording the peak responses of earthquake, which will be stored for each simulation. we then move to the generation of a demand metamodel. So what is a metamodel? To understand this, we can summarize the engineering analysis process as the research for a relationship between the input parameters of the area structure and some peak response. For example, here it might be the response, the curvature response at the base of the tower. And we usually do this by implementing finite element analysis, which, as we saw earlier, might be quite expensive in terms of computational cost. So the idea of Metamodel is to create a model of the model in the sense that we build a statistical approximation of the finite element analysis that can be run in a more efficient way in order to obtain a larger number of responses that are required to calculate the fragility functions. And an additional contribution of Metamodel is that they provide a more insightful information about the relationship between the input parameters and the response. Because, for example, sometimes we perform a finite element analysis, but we are not completely informed about the effect of different parameters on the resultant peak response. And then we use these meta models to perform logistic regression. So we start from using the meta models to sample a large number of demands that will be compared to an equivalently large number of capacities. And by this comparison, we can build a survival error vector, in which one means that the system failed according to the failure criterion we consider. And then we apply logistic regression to estimate the probability distribution of this survival error vector. So logistic regression is a technique to obtain the cumulative distribution of a binomial variable. And for us, this means that we can obtain finally the parameterized fragility functions, which, as you can see here, provide the probability of demand being higher than capacity as a function of both the intensity measure of the earthquake and also of the design parameters of the bridge, which are contained in the vector X. The next step consists in using this parameterized fragility function for optimization. The optimization problem consists in finding the best solution from a set of all feasible solutions. For example, we might start from the black configuration over here, and after performing the optimization, ending up with the orange configuration for the bridge. And to do this, we need to define two parts of the problem. The first one is the objective function that contains the response or the variable that we're interested in controlling. And then we have some boundary conditions on the input parameters. So the idea is to use these parameterized fragility functions to define either or both the objective function and the boundary conditions or the constraints of the problem. So now I will explain you I will show you how to apply this procedure by presenting a case study, which will be used to compare the performance of these optimization approaches. So the case study is Quincy Bayview Bridge, which was built in 1989 in Illinois. And as you can see, it has a main span of 274 meters and two side spans of 134 meters. The tower have a height of 71 meters from the water line and present different section changes along the leg. So in this part, we have a rectangular section, and then we have a change to a hollow section. There are then two horizontal struts, which also have a cross section, which is a hollow section. And there is a lower strut web, which is this one, that provide the structure with a higher stiffness for transversal vibration. As for the deck, you can see the details here. It consists of a steel concrete composite section with 2 main girders and 5 stringers. And then we have a concrete slab. So now we go through the process again for this specific case. The first part consists in the experimental analysis, and for that I selected a set of 80 accelerograms which can be distinguished according to the magnitude and to the distance from the source. And then I selected 11 design parameters for this bridge, which I want to optimize in the end, which are the dimensions of the cross sections that you can see here and the cross-sectional area of the cables. Here, the cables that you see with the same color will have the same area, which is what happened in the real design of this structure. And then we combine this set of accelerogram with a set of design parameters by means of random sampling to obtain the design metrics. Each one of these parameters, as you can see, the as-built ones are the one of the real bridge, which I consider as starting values. And then I selected for each of the parameters a lower bound and an upper bound within which we can apply Latin hypercube sampling to select the different realizations. So for example, x1 is the depth of this section, and I assume it to span between these two values, 3 meters and 5.75, which is a 30% variation with respect to the initial value. The next step consists in performing structural analysis. So here you can see some details about the finite element model that I built. The deck is represented by means of an elastic spine with equivalent properties of the deck cross-section, while the cables are connected to the spine by means of rigid links, as you can see here, which also support lumped masses that represent the girders, the stringers, and the traffic barrier. Then we have shell elements to model the strat web, and zero length element, which are springs, to represent the bearings which connect the deck to the lower strat of the tower. As for the tower, it is modeled by means of 2 different types of elements. The upper part consider elastic beam column elements, while the lower part, which is the one that we expect to undergo nonlinear deformation, is modeled by means of fiber sections with these constitutive laws for the reinforcement and for the core and cover concrete. Then we need to model the cables, which are represented by means of tension-only truss elements with equivalent stiffness. And now I'd like to discuss a bit more about what this cable modeling means. So if you observe the picture on the left, you might observe that cables under their own weight will sag. And this sagging results in an upper stiffness, which is different from the stiffness provided just by the material. Such stiffness will be a function of both sag and tension and inside the cable. And if we look at this graph on the right, you see that for low levels of stress, the stiffness is quite low. And then as the stress inside the cable grows, the stiffness tends to reach the stiffness provided by the material. So the way we implement to model this behavior consists in defining an equivalent elastic modulus or an equivalent stiffness, which accounts for sagging that is considered by means of the length L, which is the horizontal projection of the cable, and the internal tension, the tension force in the cable, which is this one. This surface plots the dependency of this equivalent stiffness on the length and on the internal force. So a value of 1 here means that the cable is horizontal, for which we have the higher sagging effect. Whereas when we move back to 0, it means that the cable is vertical, and in that case, we will not have a sagging contribution to the stiffness. We can also observe that as the tension inside the cable increases, the effect of sagging decays. This to say that we can model this kind of cables, this type of structures, by assigning to the constitutive law of the trusses, this equivalent modulus, and then we assign an initial stress which represent the tension after gravity loads and traffic loads are applied. The last step before launching the analysis consists in defining demand parameters, which are a quantifiable way to determine the damage inside the different components. So in my analysis, I consider damages in the towers, in the cables, and in the bearings. And for them, I assume 4 limit states, which are distinguished by the level of damage that develops. In terms of demand parameters, we first have the longitudinal and the transversal curvature ductility of the towers, the drift ratio, which is a measure of how much the peak displays during the time history analysis. Then we have the ratio between the maximum force that develops in the cables and the yielding force. And finally, the displacement of the bearings. As you can observe in the table, the bearings are assumed not to contribute to the extensive and to the collapse limit state for cable stay bridges. And this is because even if in the case of bearing unseating with respect to this pad, the bridge will still kind of sustain the loads thanks to the deck that will be supported, for example, on the lower struts over here, but also will be supported by the cables. Now we can run the time history analysis and wait for the result to be ready. And in my case, as we saw earlier in the preparation of the experimental design, I ran 160 time history analysis for the different models coupled to the different accelegrams that I selected. After this, we can start building the demand metamodels. So the first step consists in performing a linear regression analysis in order to identify which of the design parameters are statistically significant in determining the peak responses we selected. We can do that by performing, by checking, for example, the p-values of that and performing a backward selection process, based on which I remove from the further analysis the contribution of these two parameters, so the lower size of this of the cross section of the two struts and the thickness of the lower strut. And then once we're confident that all the design parameters we have are statistically significant to determine the peak responses, we can build more accurate metamodels. Here I listed the 4 metamodels that I considered. And as you can see, they can be distinguished in terms of degree of the polynomials that are implemented and in terms of presence or absence of the interaction terms. So once we have all these 4 metamodels ready, the question is how to choose the best metamodel. And we can do that by referring to some goodness of fit measures. For example, the R-square, the adjusted R-square, or the root mean square error. This graph on the right shows the comparison in terms of adjusted R-square. Every one of these vertical lines refers to one of the peak responses in the bridge. The first part refers to the peak responses in the tower, while the second one represents the peak responses in the cable. And the higher this value is, the more confident we are that the metamodel is predicting the response of the structure in an accurate way. Which means that to develop the next step, which is the logistic regression, we need to select the metamodel with the highest adjusted R-square. So by doing that, we can obtain this form for the fragility functions. Here I reported the results only for the system level fragility, but we have one of these expressions for each of the peak responses that we selected. And if, as you can see again, these are a function of both the intensity measure of earthquake and of the design parameters of the bridge. So if for the design parameters, we consider the one of the as-built bridge, which is our reference case, we can obtain the traditional shape of fragility curves conditioned only on the intensity measure of the earthquake. Now we are going to discuss about how we can use this to hide the performance-based design of cable-stay bridges. And as we discussed earlier, we can do that to hide either the trial and error updating approach or the optimization approach. So we start first by observing what we can do for the trial and error. For example, here, I investigated the effect of single parameter change on the system level fragility, which means performing a sensitivity analysis on the effect on each of the parameters we have. And to do that, I considered as measure of damage probability in the structure, the median peak ground velocity, which is the peak ground velocity corresponding to a 50% probability of exceeding the considered damage state, which means that we will have 4 different peak ground velocities, one corresponding to each of the limit states. And then I run the analysis to obtain this graph here that I will explain now. So each one of each part refers to a limit state. For example, we can just focus on the first one, which is the study on the effect of parameters on limit state 1, which is the blue curve over here. And each one on the horizontal axis, we have the variation of the median peak ground velocity resulting to the change in one of the design parameters that are on the vertical axis by plus or minus 30%. So for example, for x2, for instance, which is the short dimension of cross-section AA, this plot represents the effect of an increase of 30% for the gray part, and the effect of a reduction of 30% for the white part. The information we get about the probability of damage in the structure is that if the peak ground velocity moved rightward, we are achieving a lower probability of damage for the structure because the fragility curves move on the right, meaning that for the same level of intensity measure, the probability of damage will be lower. On the other hand, if we move leftward, we will have a higher probability of damage. So based on this, we can quickly assess what's the effect of the parameters we are considering on the system level fragility that we are studying. And we might also run this simulation to check the effect of combining parameter change on the system level fragility. The second part I want to show you is how to use these parameterized fragility functions for optimization. As we discussed earlier, this might be done considering using these parameterized fragility functions, either to define the objective function of the problem or the constraint. And by doing that, we can either minimize the probability of damage or, for example, minimize the cost while maintaining an acceptable level of damage probability. And again, to define this measure, we refer to the median peak ground velocity. So in the previous slide, we defined 4 different peak ground velocity, median peak ground velocities, one for each limit state. And to define the objective function, I refer to the average value of these 4 median peak ground velocities. And then I implemented 3 different optimization approaches that I compare to the as-built bridge. So the blue lines refer to the Quincy behavior bridge with the properties that it has now. And as you can see, on the first graph, we have the ratio between the optimal versus the initial parameters, which are x1 to x11. Then we have this second graph, which shows the average value of the median peak ground velocity. We interpreted this saying that if this bar grows, the structure has a lower probability of failure. If it moves downwards, it will have a higher probability of damage. And then we will compare the results in terms of cost. So the initial bridge has a cost of 22 billion euros, and then we will see what happens by implementing these three optimization approaches. So the first one aimed at achieving a target value of damage probability, which in this case I assume to be 0.4. And I just set the boundary on the input design parameters to range between 0.7 and 1.3 of their initial value. And as you can see, the safety, the probability of damage is reduced because this value is higher, but the cost of the structure is increased. The second optimization approach aims at minimizing the initial materials cost of the structure. So we are just considering the initial investment in material. And it aims at minimizing that while maintaining the same level of safety as the first, the structure as built now. And as you can see here, the average value of the median peak ground velocity is the same, but the cost has been reduced with respect to the starting, to the values of the starting structure. Last, in approach 3, I try to minimize the initial material cost again, but also trying to achieve a higher performance of the structure, meaning that I wanted a lower probability of failure, which again I set to be 0.4. And as you can see, the cost is reduced with respect to the initial one, but is not as low as the value we obtain just optimizing the cost of the structure and setting a lower level of safety for the bridge. So here we can see a comparison between the initial parameters and the optimal ones for the three considered approaches, which change mainly the dimension of the cross-section that are shown to be highly impactful in contributing to the cost of the structure, and or updating and changing the cross-section of the cables. So this brings me to the end of my presentations. I will first give you some conclusion. So we first observed the behavior of cable-stay bridges in case of earthquake and why they are vulnerable to this type of hazard. And then most of the presentation was about investigating how parameterized fragility function can be implemented to hide the performance-based design of cable-stay bridges in a more computationally efficient way. And we did that either to support the updating process based on the experience of the analyst, or the updating process based on optimization. And in the end, we saw an application of this procedure to a case study showing how we can achieve a seismically optimal solution in terms of minimization of the damage probability. In terms of future development, the first topic I'm working on is to include the effect of other hazards on this in this optimization. So, for example, the effect of traffic loads can be included in the boundary condition, while we also set a minimum level of safety of the structure, and we minimize the cost. And the second development will be in the definition of the performance objective. So what I present to you today is mainly related to the minimization of the probability of damage, but it can be much more impactful if the objectives can be defined in terms of, for example, losses, which are a much more meaningful variable for the decision makers. So this is the end of my presentation. Thank you very much for your attention, and I'd be happy to take any question or any feedback you have.
Thank you very much. Very interesting. Very interesting and impressive. The cost reduction was. As always, the floor is open. If anyone has any questions, please raise your hand or feel free to write it in the chat, and I will read it aloud. One question that I have, you mentioned that you randomly paired each model to only 2 ground motions. Is that true? Did I miss anything?
Yeah, that's true.
Why did you select 80 ground motions, but then you randomly, why didn't you use, I know like the finite element with 80 ground motions will be too much, but why didn't you apply the same earthquakes? Andrea, I think you froze.
And on the second. So this is why I did this set of accelegrams. But I think we can get much less scattered results selecting location-specific accelegrams. About the pairing process, I did that because I'm trying to see how we can obtain better metamodels. So the first analysis I did was by pairing, but just running 80 time history analysis. So I generated 80 different models and pair them, each one of them, to one of the accelegrams. The second approach, which is the one that I try now, consists in incrementing, kind of performing a 2 levels design for the earthquake. And I'm trying to see which of these approaches can give better metamodels. So the idea is that for a design, for example, one of them, I consider the possibility of occurrence of 2 different events to increase the randomness of that. Does that answer your question?
Yes, okay. So good luck with the next stage. I noticed I had a question regarding the traffic loading, but then in your conclusion, you mentioned that it's the next step as well. The traffic loading as well as the braking will be tricky. So good luck with that as well. Do you have any plans how you're going to apply the traffic? Would it be a uniformly distributed one or like the actual way that we design bridges?
Yeah, so about traffic loadings, I have the easiest way to do that would be just to apply a uniform load on all the span, but that will not provide the peak responses in all the components. So I'm planning to either randomly sample the distribution of traffic loads on the different spans. So for example, for one time history, I will consider the traffic load just distributed on the first part. And then for the next one, for example, it might be in the medium one, in the medium right one, or in the extreme right span. But about how to include that in the process, I think, and I'm planning to include that as a boundary condition. So for example, by controlling the peak displacement due to traffic load coming from the design configuration we are considering.
Perfect. Roberto, if you can unmute yourself and ask your question.
Hey, very nice presentation, Andrea. I really liked it, although I didn't join in the beginning, so maybe I missed something. But just out of curiosity, why do you use PGV? Why PGV is very good for this kind of bridges?
Yeah, thanks for your question, Roberto. The cable-stay bridges are structured with a very long period. And different studies on the correlation between the peak responses of this type of structures and the intensity measure of earthquakes suggested that peak ground velocity has a better correlation with them with respect to peak ground acceleration. So in this case, I use that. Another possible solution would be, for example, the spectral acceleration in the decaying part of the response spectrum, or other parameters that are more correlated with the peak responses of cable-stay bridges with respect to peak ground acceleration. And then we can, I think, in the approach I'm trying to develop, we cannot use structure-specific intensity measures. For example, the acceleration of the response spectrum at the period of the structure, because that depends and that will change on each of the iteration. So to conclude the answer to your question, it was because PGV has a higher correlation with the peak response of cable-stay bridges and generally with the response of long period structures.
Thanks a lot.
Okay. David, do you want to ask your question? Please unmute yourself.
Cool. Hi, thanks a lot, Andrea. It was really interesting for the presentation. One thing was just in response to what Arash said. Do you find a lot of variation for every single combination of the design parameters if you're only taking 2 intensity measure samples for each? Because
what do you mean, sorry, by variation?
Because so in your design space, like you've got all the X parameters, which are design variables, and you run a time history simulation for each, and you use 2 randomly selected intensity measures for every single combination of the design parameters.
Yeah, so I found a better performance of Metamodels in doing that, and that's because of the higher number of sampling points that we have. Because, for example, you see with in the different Metamodels that I consider over here, if we consider a more refined Metamodel, we also need a higher number of coefficients to be estimated, right? So to do that, it means that's also why the first step of my procedure consisted in removing statistically not significant parameters. So increasing the number of simulations from 80 to 160 improved the variability, let's say, of the response, which according to the suggested a higher prediction capacity of the Metamodels. Because when I ran the analysis only with the 18 starting time histories, the adjusted R-square was much lower than what you can observe here. And I think this can be higher, for example, if we consider a size-specific suite of ground motion.
Okay, that's great. And for the Metamodels in your final analysis, did you use an ensemble, or did you just pick the best one? And also, did you do anything to avoid overfitting? Maybe that wasn't a problem.
Yeah, it's also a point, and it's a point that comes when we select the Metamodel. So, for example, here, if I only consider 80 sample points, which means I just run 80 analyses, the Metamodel M4 had a problem of overfitting, because you see the parameters over here to be estimated would be really large. There were like 79 parameters in this model, because we are considering 11 design parameters as predictors plus the intensity measure of earthquake. So for example, if we just run 80 analyses, we cannot implement the model M4. And a similar problem stays for the model M2, which has all the interaction coefficients, right? Because it requires a really large number of parameters, but we don't have enough sample points to perform the regression. Was that your question?
Yeah, that kind of does. But did you have any like metric for evaluating how the level of overfitting, or was it kind of just you could tell when you didn't have enough parameters?
Yeah, I didn't check it. I didn't check the level of overfitting. Okay. Yeah, but it's a good suggestion to improve this. Thanks for that.
Okay, great. Well, thanks for answering the questions. It was really great presentation.
Thank you, David.
Perfect. Tom, if you want to ask your question, please.
Hi, yeah, no, thank you for a great presentation. I'm just really intrigued in the difference between the approaches and the results you got. Because in both approach 1 and 3, you set the same target damage probability. So there's clearly multiple solutions to get to that target damage probability. So I'm wondering why approach 1 chose that particular solution, because an equally valid solution would be the solution that came from approach 3. Because because they both have achieve the same target damage probability. Am I misunderstanding the results, or is your result from approach 1 just picking the first possible solution it's come to rather than showing all the possible solutions?
I'm not sure if I correctly understood your question. So approach 1 aimed at achieving a selected value of damage probability, which was the one that I call here as a big ground velocity average target. So this was the function to minimize, and the solution algorithm starts from the parameters of the initial bridge and changes the design parameter until a solution that respects the boundary conditions is obtained. I wasn't clear. Maybe your question was not that clear to me. Sorry.
I think the main difference that Tom is Tom should consider is the cost. So although approach 1 and 3 have the same, let's say, lower performance, let's call it, but the cost of approach 3 is lower when the bridge will be constructed. So you're saving money at the same risk.
Yeah, but what I'm saying is I appreciate that, but why does approach 1 give that particular solution when there are multiple possible solutions to achieve target damage? So is it that you've got the bridge already built and you're modifying a constructed bridge, or you're
yeah, exactly. In my case, I started from the Quincy bridge that I presented in the beginning, and I considered the parameters of that bridge as starting parameters. And then with the solution of the optimization process, I find the first solution that satisfies all the conditions that I set. So for example, you see that's achieved by means of a minimum variation in these parameters. But that doesn't mean it's the only solution, as you suggested, because for example, if the starting point of the optimization was below, we might have achieved a different solution, which is also respecting the boundary conditions. So it depends on the points, on the starting point of the searching algorithm. But another possibility would be to implement an algorithm that starts from different optimization points and then find the overall best solution, which I didn't do yet, but is a meaningful process to implement.
Brilliant. No, thank you for your help. I think I understand better.
Did I answer that? I'm not sure, sorry.
I think so. Yeah, no, thank you.
Thanks.
Perfect. Camila, if you want to unmute yourself and ask your question.
Hi, thanks for your presentation, Franchini. I have a question regarding your parameters. Which criteria do you use to select the upper and lower bound of each?
Yeah. So in this particular case, I allowed a variation of the parameters by 30%. I didn't make any further analysis on the relationship between them because I wanted to obtain a randomized space. But for example, an improvement of this might be when considering the reinforcement ratio as a design parameters, which will be dependent also on the other parameters. But in this specific case, I allowed a variation of 30% around the starting value for all of the parameters that I'm studying.
But why 60%?
30%, sorry.
Sorry, 30%, why?
It's not a fixed value. It's a, let's say, a reasonable interval for now, in my opinion.
Okay.
It's not a rule, which comes also from the, when you perform a design of a structure, you might have an idea about the overall size that that structure might achieve, and then you can optimize that, allowing some variation, right? And then of course you have to make all the checks to guarantee that this variation is reasonable. So for example, you might have to check the backing load in the pylons, or any other condition that might not be verified even under different loads.
All right, thank you.
Thanks.
Thank you. And Philip, if you want to unmute yourself and ask your question, please.
Hello, Andrea. Thank you for excellent presentation. I have a question regarding calculation model. Maybe this is for fundamental knowledge of bridge design, but I'm sorry, I'm not that familiar with this. You mentioned that you use rigid links to connect deck with pylon. And my first question is, so it means that you you haven't considered sogging in cables and cable strain. And the second question is, are the rigid links free of rotation at the end? Because if not, I'm curious about its effect on horizontal displacement due to lateral load of the deck. And the last question, are the cables pretensioned?
Okay, so starting from the first one, which was about the rigid link connection with cables. The sagging of cables is considered if we are using rigid links, right? Because the equivalent, this value of equivalent stiffness is assigned to each one of these truss elements. So even if we have rigid links in this part of the deck, the cable's sag is considered by means of the equivalent stiffness approach. Was that the question?
Yes, definitely. I probably it was too many new new things for me, so I missed the equation of equivalent stiffness. And I was curious throughout all the presentation, how you consider this. And so, okay, so, and yes, that definitely answered my question. So thank you very much.
I forgot the second one, sorry.
The second one was about horizontal displacement of the deck and rotation at the end of cables. But I think you have already answered this, that it's considered by equivalent stiffness. Yes, am I right?
Yeah, exactly. So the cables are not rigid, if that was the question. So
yes, definitely. This was a question.
Okay, so there are truss elements with a stiffness, so the torsion rotation of the deck is allowed. And I also remember the last question you made was about the stress in the cables. It is
that's right.
Yeah, it is included in terms of this constitutive law. So you see this value at the beginning represents the initial stress inside the cables, which might be optimized, or in my case, I just obtained that through iteration over the gravity loads.
And I see now here that there is a pretension in cables also.
Yeah, exactly.
Okay, thank you very much.
Thanks for your question.
Perfect. Can you tell me how you're applying the earthquake load as well, and where you're applying it? I might have missed it.
I'm applying the earthquake load at all the fixed points of the structure. So there will be an earthquake load here, earthquake load at the base of the two towers.
Okay, only in X direction.
Both the X and Y direction.
And Y direction. Okay, you're using the up-down component of the earthquake.
I didn't so far, but I will do after this, because I'm trying to see the effect of different parameters on the performance. And for now, I'm not considering the vertical acceleration, but I will do that in a later stage of the research. One point about that is that because of the particular response and of the high redundancy of cable stay bridges, it's usually necessary to perform this two-dimensional, to apply this two-dimensional earthquake, because the response in the two direction is strongly coupled in the response of both the deck and the towers. So that's why we need to apply earthquake in both the directions.
Okay. Valentina is asking, could you tell us what the 11 parameters you consider correspond to? I think she's referring to X1, X2's
Yeah.
dimensions, yeah?
Yeah, maybe I didn't stress on that. So the design parameters I'm considering are parameters that are frequently selected to optimize cable-stay bridges and which are particularly important for the design, which are the dimensions of all the cross sections we have along the tower. So you see we have section AA, which goes from the base until this point, which is a rectangular section. And for that, I consider both the dimension as design variables. Then we have the thickness of the hollow section here and the dimensions and the thickness of the two struts. And in addition to these parameters, which are the first 7 ones, we have the cross-section dimension of all the cables, which were grouped in different types, as you can see here, and were X8 until X11.
Perfect. So we're passing 1 o'clock. So thank you very much. Very interesting presentation. It was kind of a mini Viva as well. So hopefully you have some ideas of what might be asked during a Viva. I'll just share my screen for a second. And as always, if our speakers agree, the presentations will be available on our YouTube channel as well as EPICentre website. As I mentioned before, we'll go for a small break and we'll hopefully come back in June, July with more seminars. So thank you very much for joining this session. Andrea, thank you very much for sharing your research with us as well. And MSc students, I'll stay online after this meeting. If you have any questions, I'll be in this room for a bit more. So thank you very much, and we'll see you later.
Thank you, everyone.
Thank you.